Anyway, hello everyone. Good morning. My name is Mastinu. I'm a postdoc here at CBPR. I work also as a part-time R&D engineer at Integrum. My background is in electronic engineering. I did my bachelor and master back in Italy, and then I moved here in late 2014 to start my PhD. Yeah, sorry. To start my PhD project with Max as my main supervisor. Yeah, I guess this one. Yeah. So at the time I joined the project, the EO implant system, or the Neuromusculoskeletal prosthesis, was already a reality. So the first patient was already implanted. He was using the prosthesis at home, and that was the first time a robotic prosthesis, an arm prosthesis, was attached to the bone, the muscles and the nerves at the same time, and it was used at home, thanks to a simple but effective, purely analogic system. Okay, sorry. So my part of the picture was basically to redesign this interface, this electronic system, what we call the ALC, to basically have a more advanced signal processing opportunities as well as sensory feedback. So what you see there is basically the interface electronics between the implanted components and any robotic devices. Again, mainly for two purposes. In one direction, we need to acquire the myoelectric signals from the implanted electrodes, decode this information for intuitive prosthetic control. In the second direction, we want to basically close the loop of control. So if there's any sensor, any sensorial information available in the prosthesis, we can read it, access it, decode it, and translate this in electric pulses straight to the nerve. And this for tactile sensory feedback. We spent quite a lot of time thinking about how the system should look like, which features and stuff, and the system was actually, and we spent even more time developing the system. So we had two major hardware revisions, and the latest one being the one in the center of the slide here, the smallest one, and several versions for the software. Without going too much into the technical details, many of the features for this device were actually inspired or taken by the literature in the prosthetic field. What I would like to underline about this is that this has been designed as a basically reliable as a medical device and versatile as a research device. One of the coolest things about this system, again, it includes a neurostimulator. So if sensors are available, we can read these profiles and decode them to basically modulate pretty much every parameter in our default stimulation electric pulse that you can see here in on the right side of the slide. The result is pretty much this. You can modulate the amplitude of this electric pulse that is going to the nerve to modulate the intensity of the touch, or you can modulate the pulse width or the frequency, or basically any mixed modality. So this is what allowed our first patient, Magnus, that you can see here, to grasp delicate objects like grapes or eggs while blindfolded, without crushing them, basically. So again, all the electronics is there, self-contained, no need for extra wires or battery packs. The message here is that this project has had, since the earliest phase, a really strong push to get the technology outside the lab. So to reach the patient's houses. And I would say we quite succeeded in that. There are several patients using this technology at home. Again, prosthesis connected to the bone, the muscles, and the nerves, with intuitive prosthetic control and sensory feedback. As I said, versatile as a research device. So here, again, there's not much time for the details, but I will quickly run you through some experiments that we did thanks to this platform. Here we were playing around with myoelectric pattern recognition with conventional surface electrodes for home use. While, for instance, in this other study, we use our technological setup to basically compare the control resolution, the grasping for precision or reliability between implanted electrodes, the one of our patient, and conventional surface electrodes, the one that are basically commercially available since many, many years. Or in these other studies, connecting back to Max's slides, where we basically use this technology to experiment different strategies for improving grasping coordination. So basically, investigation about neural sensory feedback. So what's next? Well, I must say first that I had wonderful years here in Sweden on a personal level, on a working level. I had a great time working for Max, with all the team members. But as our academic career path demands, it's time for me to move on to new exciting challenges. So I'm happy to announce that at the end of the year I will be moving to Italy, more precisely to the artificial hands area of Professor Cristian Cipriani at the Scuola Superiore Sant'Anna, where I will be working on my project called END, where I'll try to develop methods for semi-autonomous prosthetic hardware, prosthetic hands. And all of this thanks to the Marie Curie Individual Fellowship European funding. And with this, I think I'll close, and I'm happy to get any question if there's time. Maybe? No?
Hello, my name is Jan Zbinden. I'm a PhD student looking into upper limb prosthetic and mostly in the control of upper limb prosthetics and embodiment. So, as has been said previously, our lab really succeeded in pushing this technology out to the homes where study participants were able to open and close their hands reliably hours and hours every day without problems. The natural continuation of just having open and close is that we want to add more degrees of freedom, so more movements for them to control. And what sounds straightforward and easy in theory is way more difficult in actual practice if it has to be reliable. So here you can see the video. This is just a couple of weeks old, where for the first time we were able to send one of our study participants home with one system that not just allows for open and closing the hand, but also wrist rotation and elbow extension and flexion. And all of these movements he does naturally, so just thinking about them. No patterns that he needs to think with, like his biceps or triceps. All of them are done naturally. And I'm very excited how his progress looks like when he comes back now after summer. Talking about natural control, the reason how this was possible, and it was also mentioned previously, is due to our strong collaboration with surgeons, where we used new surgical techniques to increase the sites for myoelectrical control. So we have now access to nerve signals that doesn't just allow for now wrist rotation, but even going as far as single finger control. And here I'm proud to show you that for the first time we have a patient with a transhumeral amputation, so above the elbow, where a lot of nerves and muscles are missing, that we still have shown that we can move single fingers. And from going from above elbow, going to transradial, so lower limb, together with our collaborators within the DTOP project, we have sent a participant home. She's been using that system for months at home now, and what you can see here is that we ask her to come to the lab and do a couple of tests so we can improve our system, both like just the prosthetic engineering part, but also that we make sure that it works in home and daily use. Talking about testing, like we want to make sure that we make a system that is useful for the users. So we act under this umbrella of prosthetic embodiment, where we want that the prosthesis feels part of a body and that the prosthesis is control as the prosthetics user want to control them. And we look into different experiments that actually help us like investigate and make our prosthetic devices even better, and thus allow for even more tasks that our participants can do at home and facilitate their life. And if there's no question,
We can do it. We can do it online. Do you want to?
635252. That's the Slido room number. 635252. Hello, my name is Kurt Stewart. I have a Master's of Science in Electrical Engineering, and I've been working here at CBPR for a few months. And the projects that I've been working on are related to the Bionic arm team, and I've been developing tests and a test bench to ensure the reliability of our system when we deliver it to a research participant. So when we have any feature changes or feature updates or new features, we want to ensure that the whole system is working. So we run through tests to ensure that we have a certain level of confidence in our system. So the system is verified through unit integration and system tests, where I've developed tests that test each line of code or each unit of code. Then we ensure the interoperability of all of these units through integration tests of the nerve stimulation, the hand open movements, the logging that we're doing, as well as the timing of the control system. And then all of these tests working together are ensured through the system tests to make sure that they are working in each mode of operation. And then as well, another project that I've been working on and completed is the phantom limb motion capture. An outcome measure that we want to look at in phantom limb pain is the movement of the phantom limb. And we want to have an outcome measure which we can validate our rehabilitation strategies. So I've developed a motion capture system, portable one that you can measure the contralateral hand, and by doing so we can measure before the rehabilitation and after the rehabilitation to ensure that there is some increase in movement, and see if that is a valid measure. So here we have the system, and we input it into a motion detection, and then we can visualize this afterwards for analysis and more research. Thank you.
Great. Good morning, everybody. My name is Dr. Eric Earley, and I am a postdoctoral researcher here at the Center for Bionics and Pain Research. I focus my research on the home use of the prosthesis as well as sensory studies with our bionic arms. So I don't think it is a stretch for me to say that most people here would be in agreement that the ability for people to use a prosthesis at home is incredibly important for this research to be able to transfer outside of the lab. And I would say that that is one of the strengths of the prosthetic system that we've developed here, is that not only can we develop new and innovative technologies, but also everything that we do immediately gets sent home and people can use this in a home environment. So not only are we creating changes in people's lives by allowing them to take this technology home, but this also means that the research doesn't end when people leave the lab. For each of these prosthetic systems, we are constantly collecting data as to how people are using their prosthetic limb. And what this means is that we can start to draw insights into how people are learning to use the limb and how the changes that we are making in the lab affect the way that they use the prosthesis at home versus in the lab. So for example, if we were to give somebody a new powered wrist, we can start to see changes in the way that they use the wrist in the lab with us watching them versus how they use it when they're at home away from our supervision. And additionally, all of the simultaneous and proportional control algorithms that Jan has been developing, we can start to see how people are learning to take advantage of that additional movement as well. So another area of research that we focus on here is on the sensory feedback, which we've talked a little bit about before. We have implanted nerve cuffs around the nerves in the residual limb that we can electrically stimulate and generate sensations that somebody feels on their missing limb. Here in the lab, we have been collaborating with Professor Johan Westbury at Gothenburg University to develop a platform with which we can track the changes to the perception that people feel, where they feel things and what it is that they feel. And we can use this to run longitudinal studies into sensory feedback and again, see how the changes that we can make in the lab affect what people feel and where they feel it. We've also been very fortunate here to work with a number of very talented researchers from around the world. So Riccardo Collu is a student at the University of Calgary in Italy. He has been investigating how the choice of neurostimulation waveform affects the perception thresholds and the quality and the location that one might feel. We've also worked with Anton Berneving here at Chalmers University in Sweden to develop and implement algorithms to remove neurostimulation artifacts, which is a common problem in a lot of implanted control systems, by developing an adaptive filter to remove these learned artifacts from the EMG to eventually improve the control of the prosthesis. And finally, we've worked with a student, Andrew Smiles, from the University of Waterloo at Canada, who has been developing slip prediction models using the sensors on commercially available prostheses to develop a model to identify when an object may be slipping out of the hand and provide feedback to the user so that they can make their own corrections to the movement to secure the object. So all in all, the system that we have here is very powerful in the way that it gives us the ability to run longitudinal and at-home studies in these different fields. And I hope that you will keep an eye out for the results from this research, hopefully coming soon. Thank you very much. I don't know if that's a good thing or a bad thing.
So the question is, what is the biggest challenge of at-home studies?
That's a really good question. I would say one of the biggest challenges of at-home studies is one being choosing the data that you want to see, because you have to think about what you want to see before you send somebody home so that you can actually make sure that you are collecting that data. And there's a balance to be had between collecting sort of quantitative data, things like prosthesis use logs and things like that, but there's also ways to balance that with qualitative data, interviews, and that sort of thing. And I don't think that fully one direction or the other is the way to go, but I think there's a balance to be had between those two. Thank you.
So hello everyone, my name is Kirsten Ahmed. I am the leg team lead. My PhD was a bone stress analysis using finite elements to optimize the design of skeletally attached amputation prostheses for transfemoral amputees. Prior to that, I had built a small physical training company where I specialized in the rehabilitation of clients with sensory motor dysfunction. So as a keen sportswoman myself, working with these people compounded the value of freedom of movement, and I became fascinated with bionic limbs. So I moved to Gothenburg a few months ago and have joined CBPR to lead the newly formed lower limb research group. For those of you who don't know the Canadian athlete Terry Fox, in 1977 he lost his right leg to an osteosarcoma and embarked on a cross-Canadian fundraiser, running a marathon each day on his favourite leg, pictured here. And I wonder if Terry dared to dream whether he would have thought it possible that in less than 50 years we would be developing bionic legs with bidirectional neuromuscular interfacing. To this aim, our group is upgrading research devices such as the open source leg from Professor Levi Hargrove's Ability Lab in the US, as well as interfacing with commercially available devices like the Otter Power Knee. So we've got three main research areas in the group. Firstly, we're developing a locomotion detection algorithm called LocoD in experiments on amputated and non-amputated individuals. You'll hear more about this from Bahara later. Secondly, together with Integrum, we're initiating a clinical investigation using a new osseointegrated implant called the e-Opera, and Alex will tell you more about that shortly. Finally, after we've achieved this, we aim to incorporate sensory feedback into our lower limb development. And for all of the clinical investigations, we have developed a multi-stage safety protocol. So the research outcome from the leg team will be an osseointegrated implant with neuromuscular interfacing, taking bioelectric signals to decode motor volition and provide neurostimulation for somatosensory perception. Thank you.
Hello, I'm Alex Thesleff, and I'm a research engineer at Inaugural, and I just finished my PhD, defending in the end of May, within the CBPR, and with Max as the main supervisor. My PhD project was neuromusculoskeletal interfacing with lower limb prosthesis. And today I'll talk a few minutes on my main focus within this project, which was on implant development. So the entire project is to, of course, to take the neuromusculoskeletal interface that we have for arm amputees and translate it into use for lower limb patients. So we'll of course want to have direct skeletal attachment, neuromuscular control, and sensory feedback. And we are in a quite good position here in Gothenburg. We have the Opera implant system that was developed here, and we have, of course, the e-Opera implant system. But one of the main challenges when going from the upper limb to the lower limb is the additional load that's placed on the implants. So in the step that when we take from the upper limb to the lower limb, we also want to increase the capacity of the implant system itself to handle these extra loads. So to understand what type of load case we are designing for, we first did measurements on our existing Opera patient population using load cells. We did simulations using OpenSim of transfemoral amputation running on the implant. We've done using this load data as input in finite element analysis to kind of figure out key parameters to focus on in the designing the new implant. And we, for example, investigated the thread profile, the depth and the root radius of the threads, how it influences the stresses in the implant, and what effect the cortical thickness of the bone has. So there was just some preliminary results from this analysis, and we found out that the cortical thickness is one of the most important factors, whereas the thread depth has moderate influence and the root radius has a bit less influence. We also found out that it's really important to keep the cortical bone support on the implant to ensure that we have reduced stress levels, not only in the bone but also in the implant itself. We're investigating different surface treatments. For example, we're investigating this low plasticity burning process to enhance the fatigue and fretting resistance of the modular interface between the fixture and the abutment. We're using a test setup that you see in the image there. It's called rotation bending test to test the implant system for many hundred thousands load cycles. And preliminary results from this study is that we saw quite major improvements using this surface treatment. So we are excited to look into this further and maybe implement it in the implant design. So this was just a few examples of the studies that we have conducted. So I'm happy to take some questions or leave to the next speaker.
If I can actually turn it on. Yes, okay. So the question is, what can you do to increase cortical bone thickness? Using EOPRA, could you perform electrical stimulation to enhance osteogenesis?
That is a very good question. So we have actually done a little bit of studies in the group. I think you'll hear a little bit about this later on. So we are investigating this. I'm not sure exactly how much you can increase using the electrical stimulation, but I'm for sure you can do it by mechanical loading. But this electrical stimulation may also be a possible alternative.
Hi everyone, I'm Ahkami and my project is a stable and reliable lower limb control with EMG signals from implanted electrodes. I'm a PhD student, just started my second year, and my project started the need of my project because the majority of amputations are lower limb and there is no commercial prosthetic legs today that control using the neural signal and they don't have any no sensation and no sensor feedback. But our team has created a technology to interface processes with the nervous system. And my job is to have reliable decoding of motor volition to control the prosthetic leg. But before starting my PhD, I was involved in a project to record from extraneural signals to enable intrusive hand movements. And we got interesting results that we show that the recorded signal from cuff electrodes are enough to decode hand movements and finger movements. And adding that data to the EMG will lead us to have less classification error in decoding finger and hand movements, which we think can be, will be useful in our research in the contouring leg. But so far, at the end of first year, I had a systematic literature review on different lower limb control methods. And in our lab, we developed a open source platform to decode hand movements by Patrick. And we decided to implement that on lower limb to decode the locomotion intentions. We call it LocoD, or locomotion decoder. That is a project that I'm working on, and I will continue working this year. Thanks.
Hey everyone, I'm Rep Musolf, and I'm doing my master's thesis at Maxis Lab. Next slide. Oh, you. So, before I get to the master's thesis, I did two side projects beforehand. The first one being a prosthetic bypass. This is a device used to mount a prosthetic to able-bodied participant to just test the prosthetic in the initial stages. This is with the idea to increase the subject population to test these prosthetics. So what I did was, using a bypass, I did a traditional prosthetic analysis using subjects with their bypass. So the publishing can be found there. And then in a similar vein, I did a lower limb prosthetic bypass. This is still in the initial stages. We hope to find similar results to the previous bypass study. And then on to my reason for being here, the open source leg. So this is my master's thesis project. Great work has been done by Professor Elliot Rouse and the people at Shirley Ryan Ability Lab. So my change in this device is an upgrade to the motors. There was a deficit found in the initial design, which I hope to remedy, which will allow full ambulation. So my specific topic in this upgrade would be analysis of the loads, similar to what Alex Thesleff talked about earlier. Questions?